Hello everybody, 'tis I from the UK, coming to you live. Just kidding, I don't have a British accent. And I'm not in the UK yet, this is pre-recorded. However, today we are talking about stellar evolution. And stellar evolution is just another way to say a star's life cycle from birth to death. So if you don't already have some, or let's just do, how many highlighters do I want? Just one highlighter today. We just want to be able to describe a star's life cycle. These two words mean the exact same thing. Stellar evolution is the fancier way to say it. From birth to death. And we can do this by comparing elements in stars to elements present in our bodies. So elements in stars and elements present in our bodies are actually very similar. We do share a lot of elements that stars have. And it's actually really, really cool because then we can say that we are technically superstars, which I think is the coolest thing about learning astronomy is how many elements we do have in common with the stars in space. The suns that burn for millions and millions of years contain a lot of the same elements that we have in our bodies. And it's just, since I am a chemistry nerd, I think it's just so fascinating to think about how many different elements we share. Like the periodic table of elements are present in literal stars in the sky, in space, millions and millions, trillions of miles away, share the same type of elements that we have in our bodies. What? That's crazy. So, let's get into it. This is so we can appreciate the very elements that make up everything around us. So my first question is, what elements are present in our everyday life? If you look around the room, you'll see the periodic table of elements. You can look at that to help you, but I'm going to give you some think time. Just a quick pause. What elements are present in our everyday life? So hopefully we have some in our brains. But the ones that are present in our everyday life include oxygen. That is what we breathe. Carbon. That's considered the building blocks of matter in general. We also have calcium. It's in our bones. Helium. Makes your voice go really, really high. Hydrogen. I'm trying to think of my periodic table. Goodness, can I think of more? Nitrogen. Magnesium. Magnesium helps you sleep, as well as zinc can also help you sleep as well. Phosphorus. Now I'm just listing some. We don't have to write all of them down. Sulfur. Oh, what about, makes our food taste really good, sodium and chlorine. So if we don't know, NaCl, that equals salt. All of these elements are present in our everyday life. And a lot of these elements are also present in the stars in the sky. So when we talk about stellar evolution, we're going to be talking about all of the elements that are present during the life cycle of a star and the ones that are in the birth and in the death. Because, let's continue to the next page, from the oxygen we breathe to the calcium in our bones, the elements present in stars are the building blocks of life itself. Which is why it is so cool that stars that go supernova, are responsible for creating many of the elements of the periodic table, including those that make up the human body. So when a star goes supernova, that's going to be that big explosion. That marks the death of a star. And they're responsible for creating the elements of the periodic table. And all of these elements of the periodic table are included in the ones that make up our human body. And so it's a really cool question. What elements do we have in common with supernovas? So take a moment, looking at this picture here, pause the video, highlight, circle, anything that you want to do, how many we share. If this is going to be our body's elements that are present in our body, and these are elements that are present in a supernova, how many do we share? Hold on, elements. How many do we share with an actual supernova explosion? Okay, let's see. Hopefully you have a number in your head. I'm going to look and see how many I can point out. So I see carbon here, and then carbon over here. You can't see me coloring it in, but carbon's on that side there as well. Hydrogen. I see hydrogen on both sides. There's a hydrogen envelope. Hydrogen fusion, as along with helium fusion. What about magnesium? That's the one I said earlier. Magnesium, oxygen fusion. Are there any more? Do we see any more? If you see more, you circle them. Oh, hold on. Think. No. I know there's one more. Hold on. Copper, fluorine. Oh, I got it. So all the way down here, these are the trace elements. Iron ash. So if you see any more, oh, I see another one. Silicon. Oh, sulfur? No. Yes, sulfur. There we go. Sulfur. Oh, there's so many. Isn't that crazy? All of these elements. So we've pointed out 1, 2, 3, 4, 5, 6. There could be many more. These are just the ones in these pictures here. We share 6 elements with supernovas. So when we look at this picture here, that's a supernova. We share elements with that there. And it's just insane to me. I don't know. I think that's the coolest thing ever, that we share elements with the supernova. Which goes to show that the elements that were present in the birth of stars throughout their whole life cycle and then into the death of stars is what helps these elements occur and what causes them to actually be created. And I know I have all my questions. The question that I constantly get when we talk about space and stars and all of this stuff is, how do we know? Because space is so far. It spans billions and billions of miles. So how do we know that this happens? Since stellar life cycles span billions of years, astronomers can figure out the progression of events, in the stellar life cycle. So these stellar life cycles span billions of years. So astronomers try and figure out the progression of events in the stellar life cycle. And the changes that occur during this stellar progression tell us about the elements in the universe. And these elements in the universe are what helps us understand that life cycle of a star. And so how does the understanding of the life cycle of a star influence our life on Earth? That's my question to you. Try and think about it. Pause the video. Write something down. Hopefully you pause the video. If you didn't, we're just continuing on. How does the understanding of the life cycle of stars influence our life on Earth? Because the life cycle of a star is very fundamental to understanding the origins of life on Earth. And because these stars are the elemental factories of the universe, so they are necessary for life, like carbon, oxygen, and iron. They are all forged in something called nuclear fusion. And I'm going to get a little bit deeper into that on the next page. But when massive stars die in supernova explosions, they're going to scatter elements across the cosmos. And then these elements become incorporated into new stars, new planets, and eventually living organisms. Really crazy, insane things. I'm telling you, this is one of my favorite things to learn about. This is, in fact, the life and death of a star. And so here is everything that you need to know about the life cycle of a star. We start as a gas and dust cloud, which is known as a nebula. And this gas and dust cloud then turns into a protostar. And that protostar, this is where nuclear fusion occurs. Nuclear fusion of hydrogen is when everything combines together. So we think of this as a combination phase. nuclear fusion occurs in that protostar. And then this nuclear fusion of hydrogen continues for billions and billions of years, which is the next the next phase of a star, which is the main sequence star. And most stars are currently in their main sequence phase. This main sequence phase lasts for billions of years. This hydrogen fusion phase, that's what causes the sun to glow and be bright, causes stars to consistently be so bright that we can see them from so far away. This nuclear fusion with this hydrogen fusing together, this combination of elements, occurs for billions of years, which is why this current stage of a star is the longest. So I'm going to write that, the longest phase. And I'm also going to write that this is what our sun is currently in, which means we have nothing to worry about. Our sun is currently in this phase because we still have a billion years to go before it burns out and starts the death cycle. So what I want us to do, if we're looking at this here, I want us to draw a dotted line all the way through these two arrows. Dotted line all the way through those two arrows. Because we're going to say that this is the life cycle of the star, and the life is going to be using the element hydrogen to be living. And then once the main sequence phase is over, that main sequence star is going to start to die. That is the death of the star. That's when the death occurs. It starts to begin. The death is when the hydrogen, the element hydrogen, starts to run out. And then this death phase occurs a lot quicker. So in this death phase, I'm going to explain that you see these two arrows. So we have a small and medium stars and then large stars. So after the main sequence phase, it starts to split off into two pathways. Our sun is going to be considered a small medium star. So small medium stars, when they start to die, they turn into a red giant. As the hydrogen starts to run out, the helium core begins to get very, very hot. And the helium core is all that is left over. Helium core is all that is left over. And that's that red giant. So as the star continues to run out of hydrogen and continues to die, it turns into a very, very hot white dwarf. And then this very, very hot white dwarf, and this phase goes pretty quickly, can then cool off into a black dwarf. And that goes into a very cold phase. And that is the life cycle of our star. Since we are going to be considered a small medium star, we follow this life cycle of the small medium stars. However, there are a lot of larger stars than ours, which is when we did that HR diagram practice and we made that graph, we saw a bunch of big stars, way bigger than our star. And then these stars followed the large star phase. So going back to here, pretending that our star, we follow the red giant to white dwarf to black dwarf. A large star is going to follow into a red supergiant. Same process, is only going to be a helium core that is left over. But since it is so big, the universe can't necessarily handle all of that all at once, which means it's going to turn into a supernova. Since it is such a big helium core for these large stars, that is going to cause the core to collapse. And these large stars let me word this in a better way. Large stars are going to be the only ones that turn into a supernova. So a small or medium star is never going to turn into a supernova. It does not follow that path of turning into a supernova. It is only going to be the large stars. They go from a red supergiant into a supernova. From there, there's two different pathways that a large star could take. It could either turn into a neutron star or a black hole. And that is where these black holes come from. And these black holes are constantly expanding, just like our universe. So they actually can get bigger and bigger and bigger, and they suck everything in their path. And that is why they're a little bit scary, because we have a lot of them on our radar, but hopefully we never have one in our path. Because if we did, we would not even have any time, and we would be sucked into that black hole. But we don't need to worry about that. All we need to worry about right now, today, in this current stage of our unit, is that we have two different pathways, one for small and medium stars and one for large stars. We go from a nebula into a protostar into a main sequence star. From there, our small and medium stars can turn into a red giant, white dwarf, then a black dwarf. However, our large stars go from a red supergiant into a supernova and then a neutron star or a black hole. So I want to go into a little bit more depth into what this life cycle includes, because looking at this picture, we have a lot of information here. But a nebula is going to be giant clouds of dust and gas. In this nebula, the gravity is going to pull every particle towards its center. And then as the mass increases, the heat is going to increase and this star is born. So this first step is going to be the nebula. These giant clouds are going to increase. And as this mass increases, our heat is increasing and our star is born. That is the first step. And then a protostar is going to be considered a developing star. So it's not going to technically be considered a star yet. This is going to be that second stage. It is a protostar. And a protostar, as the temperature rises, the nebula is going to radiate energy. And then this energy is in the form of a really long wavelength. And we know really long wavelengths are considered a red. So this long wavelength of red light is called a protostar. And so what's really important about this protostar is that all of this energy is being radiated, and we see it in terms of that long wavelength. And this long wavelength is going to be considered red because that is from what we see with our spectra, seeing all those red shifts. That's how we know that this is going to be that protostar. Then when the outward pressure balances out the inward force of gravity, a main sequence star is born. So if we look at this image over here, this pressure is going in with a force of so much pressure. However, at the same time, we have elements pushing outward, causing this force to go out. So when this pressure finally begins to balance out, the main sequence star is formed. And this is 90% of a star's life. So like I said, our sun is currently in its main sequence phase. And this is going to be for a long time. And most stars are in their main sequence phase. And that is why we can see them burn so bright, is because of that pressure balancing out and causing that energy to continue to flow. And this is where it starts to we decipher between the small and medium stars versus large stars. So I'm going to start with the small and medium stars. They turn into a red giant. So as they start to die, all the hydrogen is used up, and the core contracts and the star expands. And this expansion can lead into a white dwarf and then a black dwarf. So when a star runs out of this hydrogen, it's going to whoa, what happened there? It's going to shed its outer layer. And then, sorry guys, I cannot talk today. And then the star will completely cool off into a black dwarf. So this death phase, like I said before, happens pretty quickly because all the hydrogen is used up. It is going to contract and then expand. And when the star finally runs out, it's going to shed its outer layer. Then when it's completely cooled off, we call that a black dwarf. Going over, so restarting, we're in our main sequence phase. For large stars, they turn into a supergiant, a red supergiant. And in order to get a picture of this, that is 1,000 times larger than our sun. So these are really, really large stars. And then from the red supergiant, the only thing that they can do is turn into a supernova. And that's a very rare, brilliant explosion. And it's the collapse of a star sending a shock wave from the star's interior. And this shock wave is what causes those black holes to form. So we don't really go into what a neutron star is. We're just going to go right from a supernova into a black hole. But like I said, it's very rare. That's why we don't have a lot, because supernovas usually have lots of elements becoming present when they are expanded and exploded. And that happens not very often, which is why we don't need to worry too much about a black hole. These are dense objects with gravity so strong that no light can escape. We don't need to worry too much about that. I know when I was in high school learning about this, I got really scared of black holes, but that's okay. They are not as scary as you think they are. They're really, really, really like so far away that we don't have to worry about them. But these are our notes. Go ahead, put them in the notes section of your binder. And then the sub will have something else to pass out to you that you will work on for the rest of class and then turn in at the end. If you don't finish it, it's homework, but I'll see you soon. Bye.